All right, so we had a treat from Shay yesterday, and today he give us another treat with double the time. So about generalization theory in machine learning.
Right. So hello everyone, and I'm just trying to somehow make so I can see you better. This is as loud as it can be. Okay. Okay. So yes, I'll see you like that. Okay. So thanks everyone for coming. Unfortunately, I can't see you too well, but we'll manage with what we can. So yeah, so today we'll tell you about my main area of study, which is learning theory, and in particular what we call generalization. As I said yesterday, but mostly Avi listened, I hope that this talk will be interactive. So if you have questions, please don't shy away and stop me. And again, since we have 2 hours, I'll also try to include some technical arguments and not just to survey the area. Okay, so let's. I will not assume anything, by the way. So we'll just assume knowledge of probability theory and combinatorics. Okay, so so let's start. So first of all, from a very high level, so what is generalization? So generalization maybe is the defining property of machine learning, right? So a machine learning algorithm, what it does, it is trained, it gets as a training set, as input, it gets a bunch of examples which specifies some wanted behavior. So say, let's say, to classify images, whether they contain a car or I don't know, or a bus. And then it outputs, what it outputs is a function, is actually another algorithm. It outputs a new algorithm, and this new algorithm is supposed to classify correctly or to predict correctly new unseen example. Right, so you can think about it that we try to learn this function, this general function. We get to see a finite partial subset of this function, so a finite partial function, and we generalize to unseen points. In a way that approximates the target function that we try to learn. So this is generalization, the ability to correctly predict on new data that was not part of the training set. Now, what inspires much of learning theory today is that the traditional machine learning theory, and in some sense even the traditional principles of statistics, they do not explain generalization in modern algorithms. We will expand on this. But in a nutshell, one main reason that has been explored is because the traditional theory is based on a worst case perspective, right? Studying the worst case is very convenient mathematically because we just have a universal quantifier that should in a bit more detail, this worst case perspective reduces the task of generalizing, of learning, to optimization, to empirical risk minimization over restricted classes of algorithms. And this is in contrast with what we see in practice, in particular in the area of deep learning, where the functions we use, the algorithms that our machine learning algorithm outputs, the classifier that the algorithm outputs is very, very big, is a very complicated algorithm. And I think this fact is actually, as a scientist and as a mathematician, I think it poses really exciting and interesting research opportunities. And I hope I'll convince you that this is indeed the case by the end of this talk. Now, one thing that me and maybe my co-authors, one main difference between my research and maybe the more common research in machine learning theory is that rather than trying to study what the dynamics of let's say deep learning algorithms, which are the main workhorse these days, I actually take the opposite approach and I try to revisit the theoretical foundations, so the very basic definitions of what does it mean to learn, how do we order the quantifiers in the definition of learnability, and so on. And the goal, of course, is to reach a more general theory that can model, circumvent that worst case perspective and aim to a more every case sort of theory.
What do you mean by every case? Every case includes also worst case, right? So
every case means that okay. I hope this will be answered soon. Okay, we will see examples of what I mean by that. But in general, what it means is that the analysis, the way you analyze, let's say, an algorithm will not be with respect to its worst case input. This is just as an illustration, but rather something a bit more. But we will see this soon. Okay, let's I think this will be answered soon. Okay, what I will show you today is two attempts to do so. Both are works from I guess 2 years ago now, and it is with this wonderful team of superstars. So let me, okay, so our plan today is as follows. At first, we will discuss the traditional pack learning theory. We will define it properly. I hope to also, as a warm-up, to do a short example in this context. And then we'll discuss the two variations of pack learning theory, which we developed in these papers. And both of them attempt to modify the worst case perspective to an every case perspective, to a more flexible and more expressive theory. Okay, so let's begin with the classical traditional pack learning. So let's begin with the most basic definition. So what is a learning problem in pack learning? So a learning problem is simply a distribution P over ordered pairs of points from X, which we call instances, and labels. And in this talk, we will assume that the labels are discrete and binary. So we have 0 and 1. So you can think about maybe the points X are images from the internet, and the labels indicate whether the image contains an animal or does not contain an animal. And what is a learning algorithm? So mathematically, it is a function. The input of this function is a sequence of n examples, ordered pairs that are drawn IID from the distribution P. And the output is a classifier that attempts to label all possible instances, all possible points from X. And what is the goal? What is the goal in learning? So the goal is that the classifier that we output has a low error on random examples that are drawn from the same probability distribution. Right? So notice that the input examples and that the error are tested on are coupled, right? We get the input examples from the same distribution on which we are tested. Okay. Now the classical or traditional object that is used in order to quantify generalization is what we call learning curve. So the learning curve is something that is a function of an algorithm and a problem and a distribution. And it simply describes for every n what is the error, the expected error of the algorithm after after training on n examples from the distribution. Okay, so this is the learning curve, right? So for every algorithm and for every learning problem, we have this learning curve, which is simply a sequence, right? We think about it as a curve, but formally it is a sequence of real numbers between 0 and 1. And the nth element in the sequence is the expected error of the algorithm after being trained on n examples. And with this object is used both in practice and is studied also in theory to quantify generalization. Okay? Okay, great. So now we get to the definition of PAC learnability. So in PAC learnability, it is assumed that there is a class of functions, which we call an hypothesis class or a concept class. And this class of functions is known to the algorithm. And we further assume that the target distribution is realizable by the class. What this means essentially is that there is a function in the class that has 0 error, that with probability 1 predicts correct on a random example. Okay, I said essentially because it's infimum rather than a minimum, but it's really not a critical point. Right, so the algorithm knows that the target function is taken from a given class H, capital H. And then here is the definition of PAC learnability. So we say that H is PAC learnable if there is a vanishing bound, there is a sequence R of n that goes to 0, such that for every realizable distribution P, the expected error after seeing n examples from P is bounded by this R of n. Right, so notice that this definition is distribution free in the sense that the same bound R applies simultaneously to all distributions P. Right, so all learning curves, they are dominated by this curve that goes to 0. All realizable learning curves are simultaneously dominated by the same R of n, which goes to 0. And this is exactly this is exactly the worst case nature of PAC learnability. Right, you could, and we will soon, consider a different definition in which for different distributions, you have a different rate in which the curve goes to 0. Any questions? Okay, good. So, okay, so here is a fundamental question which will guide our talk. So we have a mathematical definition of when a class of functions is learnable. So this immediately raises two questions. The first one is which hypothesis classes are learnable? Can we mathematically characterize them? Is there a simple description of these classes? And the second question, which is not less important, is algorithmically, how do we learn? What are the principles of generalization, of good generalization? Before we answer this question, I want to maybe do a quick example together and to study a very simple class, and together we'll prove that it's PAC learnable. And along the way, I'll also demonstrate a very powerful and elegant technique of symmetrization that is very common in learning theory. Would you like to do it? Something a bit more technical? Okay, so now I need to move to the iPad, so I think what I'll do, I'll just temporarily disconnect and connect here. How it would be nicer to be over there.
Next time.
Next time, yeah, hopefully soon, Avi.
Yeah.
Okay, so so let's do this example. So the class will be H. Okay, wait there. H is going to be HT for a T in let's say R, where HT of a point X equals 1 if X is less than T, and 0 otherwise. Okay, so we have this this class. So a typical hypothesis in the class looks as follows, right? So somewhere we have the threshold T, and then until T we have 1, and from T onwards we have 0. Okay. Okay. So now I want that together we will construct a learning rule, a learning algorithm for this class. So what is a learning algorithm? We need to describe which hypothesis it outputs given n examples, given a sequence of n examples, and we only restrict ourselves to realizable distributions. Right, so we assume that the target function is indeed some threshold function. Okay, so so how will the training set, the input look like? So it will look like this, right? So we will have some maybe x1, x2, x3, and so on. And here we'll have xn. And then maybe here the label will be 1, here the label will be 1, here the label will be 1, and somewhere maybe here x3n over 4, the label will become 0, and it will remain 0. So here we have x3n over 4 minus 1, here it is still 1. Right, so this is how a typical training set looks like. Which classifier, so given this training set, this input, which classifier would be natural to output, which function? Can you suggest anything?
You have to ask harder questions, I think.
Okay, good. So so one possible classifier would be, let's say, take this point, right? So take the middle point, let's say, where the sign change occurs, and output the threshold consistent with this point, right? So learning rule, given realizable. Realizable means that it is consistent with some threshold. Realizable input sample, output the threshold, corresponding to the average of rightmost one labeled example and leftmost zero labeled example. Okay. Now I'll ask you a harder question. So I claim that this learning rule satisfies the following: the expected, so for every realizable distribution P, for every realizable P, the expected error of Hn is at most 2 over n plus 1. So I claim that for every realizable distribution, if you feed it n examples and ask what is the expected error, then the answer is at most 2 over n plus 1. And I want, and there is a very simple and calculation-less proof to this fact, which I want to share with you. And as I said, it also demonstrates a very useful technique of symmetrization. Okay, so what do we need to prove? So we need to prove so that if we sample x1, y1, xn, yn from P, and then we compute A of this, we apply the algorithm on this sample, xi, yi. This is Hn, right? So we compute Hn, and then we sample a new point xy independently from P. And then in the end, we test whether Hn of x equals y. Right, so we want to see, oh, not equal to y. We want to show, that the probability of this event is at most 2 over n plus 1. And the probability is taken over everything, over sampling the n points and over sampling the test point, and right, so the probability is taken over everything. So now this is a more interesting question. So how can you prove it without any calculations? Just with using that IID samples are you know, a permutation of an IID sample is an IID sample, what we call symmetrization. Anyone sees? Okay, so let me show you. So instead of doing this experiment, let's imagine a different experiment, which is equivalent, which is statistically equivalent. So the different experiment, equivalent experiment. So first, instead of sampling n points, we are going to sample n plus 1 points. Sample n plus 1 points, x1, y1, up to xn, yn, and then another one, xn plus 1, yn plus 1 from P. Then, after we sample this n plus 1 points, we're just going to pick a random example from this n plus 1 points as the test example. So sample uniformly I, an index of the test example from n+1, then compute Hn, which is the algorithm applied on everything but the ith example, xi, yi we remove, and up to xn+1, yn+1. Okay, so we compute Hn on everything but the test example, and then we test whether Hn of xi is equal to yi. So do you agree that these two experiments, these two statistical experiments are equivalent? The expectation of the events written in item 4 are the same. The probability that the event in item 4 holds is the same. Right, it's the same because the only thing we used here is that when you sample n+1 IID examples and reorder them, you still have a distribution over n+1 IID examples, no matter how you reorder them. What is it called? It has a name, this property of IID. I forget. Not only IID distributions have this property that you can permute them and get the same distribution, and there is a name for this, but this is the only thing we use, right? But what is the advantage now? Let's pause the experiment after item 1. Let's pause the second experiment after item 1. So what do we have? We have now n+1 examples. Maybe this one is labeled 1, and this one maybe is also labeled 1, and so on. And then at some point we have xi plus 1, and this one is labeled 1, and here we get 0, and then we get all the way to xn+1, which is also 0. This is how it looks.
This I is j, maybe, no?
Thank you. This I is j. Right, so the xj is where the sign change happens. So this is how the picture looks after item 1. And now what will happen? We will pick a random example from these n+1 examples. We will hide it from the algorithm, train it on the rest, and then test whether we make a mistake. For which examples, what are the bad examples that if we happen to pick them, the algorithm might make a mistake? Is x1 a bad example? Is x1, y1 a bad example? It's not, right? Because if we hide it, the algorithm will return the threshold corresponding to this guy, which we label x1 correctly. So if you think about it, there are only possibly two bad examples, which are xj and xj+1. So after conditioning on the first step, there are at most two examples which can fail our algorithm, which will cause a mistake in item 4. And therefore, formally to prove this, so you just condition on the n+1 samples, and then you say that for every fixed fixing of this conditioning, the probability is at most 2 over n+1, and therefore also when you integrate over the n+1 examples, you get a bound of 2 over n+1. And this trick of symmetrization, right, of changing the experiment and using symmetry is very, very useful in learning theory. If you want, in the end, I'll tell you a nice puzzle, very confusing puzzle related to symmetrization. But for now, let's continue with our talk. Share screen. Okay. Okay, so we showed one example of learnable hypothesis class, and we showed that an algorithm that demonstrates that the learning rate is at most 2 over n plus 1. Okay, so now let's go back to our more general question. Which function classes are learnable and how?
Maybe one should stress that it's amazing that such a general question has an answer.
Right. I mean, not a tautological answer. Yes,
Yeah.
it is. Right. So what Avi says is that if you look at this definition of learnability, and just as a mathematician, it doesn't look like the most, I don't know, elegant definition, to just study when you're bored. But nevertheless, it is captured by, as we will immediately see, it is captured by it has a very appealing and simple characterization. Okay, so let's answer. So here is what is called the fundamental theorem of Pak learning, and what it says is that Pak learnable classes are exactly those classes that have finite VC dimension. So what is the VC dimension? So the VC dimension is a number that we associate to every class of functions. It's a natural number, it can be infinity. And so let's define it. So the VC dimension is the maximum integer D, such that there exist D points, x1 up to xd, so that when you project, you restrict all your functions to these D points, right? So you look at all possible vectors of length D, h of x1 up to h of xd, where h is in your class, then you get the entire Boolean, D-dimensional Boolean cube.
Do you have a picture, Shai? If not, I'll just draw it.
Can I see?
There's a picture now. No, yeah, I don't know if you can see. Yeah, so for every h, we put a 0, and every x, we put a 0 if h of x is 0 or 1. Okay, so this definition, so it's a matrix, maybe infinite matrix, and the VC dimension is D. It draw them consecutively, but they can be anywhere, so that you see in some order, you see all the Boolean sequences. This is the projection. So if you look just at the submatrix induced on this D column, x1 up to xd, you see the truth to the D combination. So the largest D is the VC dimension of this matrix, of this hypothesis class.
And it is a
Yes,
very... Sorry?
you can guess what I do.
Yes. You explained, I can imagine it. So, and by the way, a nice problem is to calculate the VC dimension of, geometrically defined classes. So for example, okay, so for thresholds, the class we discussed earlier, the VC dimension is 1, or it's 1, right? Because you can never see, right? We had 1 and then continued by a 0, so you can never see 0, 1, right? So you cannot shatter 2 points because you can never see 0 followed by a 1. But more generally, for half spaces, it is D or D plus 1 if you take symmetric, and this is a nice problem to prove it. Okay. So this theorem indeed answers the first question of mathematically which classes are learnable. We have a very concise and simple combinatorial characterization of those classes using the VC dimension. And moreover, you can show or the proof implies that the optimal learning rate in the definition of Pak learnability is D over N. right? So there exists an algorithm such that for every realizable distribution, if you give it n examples, it will the error of its classifier will be at most d over n, and this is tied up to multiplicative constant. There is also a lower bound of d over n over 2 or something. Okay.
I have a question. You cite two papers. So what's the 1989 paper about then?
A good question.
The first paper in the West that did the same thing. I mean, the whole result and proof were in the Vapnik-Chervonenkis paper.
Right. So Vapnik and Chervonenkis, they studied it more from the perspective of statistics. So in the next slide, we will see their main result, and I think pack learnability, as we defined it, or similar to it, was defined only in the 80s in the West. And the second paper basically figured out, and in some sense, I think even translated the first paper and realized that they have results in statistics or probability theory that are relevant to learning theory.
Not relevant, it's equivalent. I mean, it's not I mean, pack learning was a new name for an object that Vapnik and Chervonenkis really defined and proved the theorem. I think that Valiant didn't know about their paper when he defined the pack learnability, and these four authors did know about Vapnik and Chervonenkis, and they credit.
But I think also Vapnik and Chervonenkis focused really on uniform laws of large numbers, and less
the same statement. They didn't call it like this, but it's the same statement.
So this is exactly my next slide. So right, so we have two questions: what is learnable and how?
So one more thing, because before how, you are now going to talk about how, right?
Yes.
Yeah. So just to say that the proof of this theorem of Vapnik and Chervonenkis uses the symmetrization argument, which is somewhat more complex than what Shay did, but in the same spirit.
Right.
It's very, very clever.
Yes, indeed, very clever. Okay, so how to learn? So the proof, and indeed the proof of Vapnik and Chervonenkis, tells us the following very simple and intuitive principle. Basically, what you need to do is output any hypothesis H from the class itself, which is consistent with the input, which has zero error on the input in the realizable case. All right, so just output any interpolating hypothesis from the class. Right, so you can forget about all these generalization and probability theory and IID. You just have an optimization problem. You get an input sample, and you need to compute an hypothesis which interpolates the input. Hypothesis from the class, of course. And this follows indeed from this very seminal result by Vapnik and Chervonenkis. And we also use this result, for those of you who were yesterday, we also use this result in the Minimax. So let's read it together carefully. What the result says is that whenever you have a class H with a finite VC dimension, let's denote it by D, then for any distribution, it doesn't have to be realizable. It can be any distribution over examples, over pairs XY. With high probability, the following event holds. And the event says that for every hypothesis in the class, the population loss of the hypothesis, this R of H, right, the probability that it misclassifies a random example, and the empirical loss of the hypothesis, right, so the fraction of examples from the training that it misclassified, are roughly the same. So what you see, the empirical loss, is what you get. The population loss up to a small error that vanishes as n goes to infinity.
I have a question. On a previous slide, didn't you say the optimal error rate was d over n without the square?
let me address it. Let me address it soon. Before I want to touch upon one point. The beautiful and the fact about this result is that if I would remove this quantifier for every h in H here before with high probability, this would be a very easy statement, right? If for a fixed H, the fact that the empirical error and the true error are very close to one another with high probability, this is simply a concentration inequality for tossing a coin. Right? If the probability of making an error is p, and you sample n examples, then on p times n of them, you expect to see an error, and we know exactly how it's concentrated very fast. What this theorem tells you is that you can switch the quantifiers. You can move the for all h in H after the with high probability. And this is exactly what allows you to optimize, because it tells you forget about the population loss, right? What you want to minimize is the population loss, this error of H. Forget about it. The empirical loss, what you see, is a good enough proxy of it. And now about the question that I was asked. So here indeed we have square root d over n, and before I told you about d over n, and indeed this result does not quantitatively imply the result that I wrote in the previous slide. But the result I wrote in the previous slide only applies to the realizable case, when we assume that there is a distribution, that the distribution, there is an hypothesis with zero error. And when this is the case, there is a variant of this theorem where the square root d over n is replaced essentially with a d over n. Okay, but I don't want to get into these details. It's not. Any questions? Okay, great. Okay, so the take-home algorithmic principle of this fundamental theorem of back learning is that it reduces generalization to optimization. It suffices to find an hypothesis in H that minimizes the sample error. If you minimize the sample error, then you also approximately minimize the population error.
This is sometimes called Occam's razor. You take the simplest explanation you can, and it's as good as any. The simplest explanation is just consistency with the sample.
I just remembered the footnote in your book about Occam razor, which I recommend all of you to read it. Avi has a chapter in his book about Occam razor, and he cites the original Occam razor, and how does it go? Like entities should not something. Avi, do you remember?
What William of Occam wrote in whatever the 16th century, I don't know when, in Old English, it's a complicated sentence. It's really complicated. Things should not be multiplied, whatever.
Entities should
the question is, how these people interpret it as the simplest explanation is the best one. And the answer to this is they apply the Occam's razor.
Yes. Okay. Good. So okay. So now let's discuss a little bit in what sense this theory of back learning does not explain generalization in modern algorithms.
Can I say one more thing, Richard?
Of course, Avi, of course.
Yes, so this Occam's razor, this way to find basically the optimal hypothesis is not always sufficient. We don't know, there are problems for which it is hard to solve. So even though some hypothesis class may have an algorithm like this may need exponential time to actually find a good hypothesis. It does not guarantee efficiency, and Valiant, this paper is the difference from Vapnik-Chervonenkis is it focuses on hypothesis classes, or we challenge it, finding hypothesis classes for which we can actually find the hypothesis efficiently. And yeah, that we don't understand.
Thanks. Okay, so now I want to tell you a little bit, really briefly, about some experimental work demonstrate this theory of back learning and in particular this principle does not apply in modern learning algorithms. So, so one such work from 2016 by Zhang, Bengio, Hart, Recht, and Vinyals, what they did is that they took a deep learning model, deep neural network, and what they did is they took a simple problem. So let's just, for the sake of discussion, imagine the problem of classifying a handwritten digit, right? So people write just write using a pen a digit from 0 to 9, and the computer should, the algorithm, the classifier should identify what the digit is. Okay, so the examples are you have the handwritten image, and the true label is what digit is this image is. So what they did is that they trained these algorithms, but they injected various level of noise. What does this mean? So fix some parameter p between 0 and 1. And what they did in the training is that when you get an example, then with probability p, you flip the label to a uniformly chosen label between 0 and 9. Right? So you toss a coin, and with probability p, first you get an example where you see, let's say, a 4, the digit 4 written in handwrite, and next to it there is the correct label which says this is indeed 4. But now what you do is that probability p, you pollute it. You take this 4, the label 4, and you change it to a random label between 0 and 9. And they did it with various p's, right? So they did it with many noise levels p. Right, so when p is 0, you just get noiseless data, you just get the examples as they are. But when p is 1, then you simply get random noise, you get nothing. And what they observed is something amazing. The sample error, right, so you train the algorithm, it spits out this huge neural network. And then you can check how this neural network behaves on the training data and how it behaves on the test data, on new drawn examples. And what they observe is that the sample error was always 0. Even on those examples that were corrupted, it basically interpolated the noise. It overfit to the noise, always. No matter what P was, always the sample error was consistently 0. However, the test error was also always optimal, right? So optimal means that right, every classifier errs with probability p times 9/10 or something, and this was approximately the error of the neural network that they trained.
What is, when you say sample error was 0, for what hypothesis?
No. So you train. So you have n examples from this.
This is the output. They trained the network, and this is what the network did. It made no error on the sample, and it was optimal on the rest.
Exactly. It interpolated even the noisy examples on the sample. So the training error was always 0, but the population loss was, of course, it cannot be 0 because with probability p you get a random noise. It was always optimal, but in particular it was far away from the training error. Training error is 0, and the population error is roughly p times 9/10. And this shows you that this principle of what you see is what you get, right? That the training loss is a good proxy of the population loss does not hold for these algorithms.
Yeah, sorry. So I thought these theorems assumed that the functions were learnable, so they should have error 0. But this function with noise, I guess you could.
Yeah, it's a new model. Now
Right,
there is
okay.
noise. The data.
Exactly. That's exactly the point.
algorithm is different, it's noisy. Beforehand, it
Right.
was pure.
But I guess, so for that reason, why would you expect those theorems to hold?
You don't, it's
Okay.
just, but there, it was first observed empirically.
The point is as follows. So, you know, traditional learning theory and statistic, they would tell you, look, what you want is to use models that are not too simple because you want them to be expressive enough to capture the you know, to express the learned function to be useful, but you don't want them to be too complicated because then you start overfit. Then you will start to just interpolate the noise, and you know, this is going to be useless. So you need to find the sweet spot of, you know, just exactly the right complexity of the model, which is enough to capture the patterns of the data, but not too expressive that it will overfit the noise. That was the philosophy. And here we see that something else is happening, right? You overfit, right? If you look at it from a traditional lens, you completely overfit because you do, as we see here, the sample error is always 0, and yet you learn. And this was a big surprise and shock in the machine learning community. Now, before we move to the works I actually want to present you, I want to give you a very simple example of a classical learning algorithm that precedes Vapnik-Chervonenkis, Valiant, everyone. The first learning algorithm, maybe, that also has this property. Anyone has an idea? The first learning algorithm there was from the 50s.
Perfect.
No, even before the perceptron, I think. Okay, I will try to say it. And if we'll need, we move to the iPad. I don't want to. So the algorithm is one nearest neighbor. What is one nearest neighbor? So we assume that the domain is a metric space. So domain X is a metric space. And one nearest neighbor, you know, it gets the sequence of examples, x1, y1, x2, y2, up to xn, yn. And then it gets a new test point x. From the name one nearest neighbor, what will be the label of x? What will you predict on x? Anyone? Shall I use the iPad? Will it be? I'm afraid that. Let's use the iPad. Okay, so one nearest neighbor, right? So we have this metric space, and then we get this example. So x1, and let's say the label is 1. And then we get x2, and let's say the label is 0. And then somewhere here is x3. And x3, and the label is also 1, and so on. And here we have xn, and the label is, let's say, also 1. And then you get a new test point x. How will you label it? What you do is you look at the nearest neighbor of x, and you borrow the label from the nearest neighbor. Okay, so this is the algorithm. And now I claim that this algorithm also has the property that the sample error, right? So imagine a continuous distribution. The sample error is always going to be 0, right? Right, because if you get the same example, of course, it will be the nearest neighbor of itself. However, already in the 50s, mathematicians knew how to prove that this algorithm, in fact, learns any distribution. Not in the PAC sense, not in the distribution-free sense, but it learns any distribution in the sense that the learning curve always approaches 0 for noiseless distributions.
But the metric is given, and then you quantify overall distribution.
Right, so the metric is given, and the metric, if you want to be formal, the metric defines the sigma algebra and the set of distributions, and yes, and then you get Yeah, the metric defines the problem, the learning problems. Okay, how do I stop? I'm trying to, okay, share screen.
So who analyzed this?
Just a sec. I'm not actually. I'm not sure, Avi. I think Cover has one proof, but I don't know who was the first to analyze. I don't think Cover was the first.
Cover was not in the 50s.
Yes. So I think it's before. Okay, so again, so this is just to show you that this, this shocking phenomena actually has been observed in theory 70 years before, or 60 years before. And but again, in a different setting than the PAC setting, right? It's in this, and this brings us to the next topic, which is this theory of universal learning. And here I will try to give one answer or one demonstration to Zev's question of how we relax the worst case nature of PAC learning. Okay, good. Okay. So let's recall the definition of PAC learnability. So H is PAC learnable at rate R if there exists an algorithm so that for every realizable distribution P, all learning curves, the realizable learning curve is at most R of n, is at most this rate. And we know that the optimal rate is the VC dimension over n. And we said that this definition is distribution free. The same rate applies uniformly to all realizable learning curves. We have one algorithm whose learning rate does not depend on the distribution. It only depends on the VC dimension and the number of examples. So it's natural to maybe allow for some dependence on the distribution. So let's consider the following definition. So we will say that the class H is learnable at a universal rate R, and it starts similar. So there exists an algorithm such that for every realizable distribution, there exist distribution-dependent constants, right? So we have this capital C and small c. And for every n, the learning curve will be bounded by this order of R of n, right? So it's capital C times R of, so the reason we have small c is for technical reasons, but morally what it says is that, you have a constant that might depend on the distribution, but otherwise the asymptotic of the learning curve is the same. Okay, so if we compare it to the definition of PAC learning, we see that we only added these distribution-dependent constants.
Wouldn't this be the same just with a slightly bigger R?
No, it won't. We'll soon see the main result here. But is the definition clear? Right, so the order of quantifiers is clear. So we have an algorithm, and then for every P, so R exists, R is fixed. We are learnable at rate R if there exists an algorithm such that for every P, there are these distribution-dependent constants, and then for every n, as n goes to infinity, the rate is at most C times R of small c times n. Okay. So pictorially, what happens here is that, and what we will soon see, is that really the PAC, the R of n from PAC learning is the upper envelope of the distribution-dependent learning curve. And what we will see soon is that there are classes H for which every distribution-dependent learning curve, right? We have an algorithm such that every learning curve individually decays exponentially fast, decays extremely fast. But when you restrict yourself to only study the upper envelope, as per the PAC definition, you will get this blue curve, which is linearly, which drops linearly to zero. Rather than
Shy, D is B?
Yeah, D should be P. I'm sorry. D should be P. Okay. D here is the realizable distribution, and in pack learning, you want to dominate. You want a bound R that dominates all realizable learning curves. And in universal learning, you allow yourself a little bit more flexibility that enables to study the asymptotic of individual learning curves.
Shot?
And yes,
So without the little c, you wouldn't be able to get this?
without what?
Without the small c, this wouldn't be possible, right?
That is correct, especially for the exponential case. In the exponential case,
Right. So okay.
yes. I didn't add it just for the complexity. Okay. Okay, so Zev, does this address your question from before? How, to some extent, we move from the worst case, this blue curve, to every case?
I understand. I think that maybe the choice of name is maybe confusing, but
okay, good. Okay, so here is the main theorem we proved. So we proved a trichotomy. So we proved that every class H in the world satisfies one of these. Either H is learnable at an optimal rate of which is exponential, else H might be learnable by an optimal rate which is linear, 1 over n. This is like the VC case, the pack learning case. And the third option is that H requires arbitrarily slow rates. And there are two comments I want to say about this theorem.
H which is learnable at all?
No. Okay, so this is the first comment. So first of all, in this definition, every H is learnable, right? So this is the result about one nearest neighbor from the 50s.
But a rate you mean that it goes to 0.
So let me so what I mean is that when I say every H is learnable, I mean that there exists an algorithm like one nearest neighbor that for every distribution, every distribution labeled by any function, the learning curve will eventually go to 0. And what the third item says is that for some classes, this eventually can be arbitrarily slow, in the sense that if the class is the class of all functions, then and you give me an algorithm, then for every rate that goes to 0, I can find a distribution in which the rate of the algorithm will be even slower.
I mean, the metric case is not relevant here. You are not talking about metric spaces. So take H to be the class of all functions on an infinite set. This is not learnable.
It is learnable. It is learnable. Okay, there are some measured theoretic assumptions, but let's assume a countable domain. Okay, in the countable domain, it's even simpler. If you have a countable domain, take the class, let's say the natural numbers, that the class of all functions is learnable, and this even happens by the simple algorithm that just interpolates, right? So on the data, on the examples it sees, it labels according to what it sees, and otherwise it just predicts 0. What will happen is that for any fixed distribution, when you see more and more examples, eventually you will consume the entire space. You will see all but 1 minus epsilon.
No, but it's countable. What do you mean you will see the example? It's countable. You will only see a finite number of points. You will always miss almost everything.
No, but the probability mass will go to 0.
But you have a distribution.
The probability mass will go to 0. Okay, very good. Got it. Okay.
Countable case.
Okay. No problem. So anyway, for point 3, the example is all functions.
Yeah, the class of all functions satisfies item number 3, and you could treat those as not learnable, if you will, because there is no rate for them. Okay, so this is one comment. The second comment I want to say is about item 1. If you think about it, even if even let's say we play the following game. You try to learn some distribution, and I tell you, look, I'm going to help you. I know the target function. This is what it is, h. Believe me, this is what it is. I give you the target function. If you don't trust me, just to verify that I didn't fool you, you will need linear one. Let's say you want to verify that my error is less than epsilon. You will need roughly one over epsilon examples just to verify this. If you don't trust me, right? If there is an oracle that gives you the target function and you don't trust this oracle, you will need a linear number of examples to verify this. So what we see in these classes in item 1 that are learnable in exponential rate, we see that in some sense, the search problem, finding a good hypothesis, is easier than the verification problem of verifying that a given hypothesis is good. And I think, and of course, this is not the only place where this phenomena happens, but I think it's interesting, and it was counterintuitive to me when we encountered it.
If it's pack learnable, then it has to be 1 or 2. Is that right?
No, that's not true also. So it's actually, so if it's pack learnable, sorry, maybe what you said is, I'm sorry. If it's pack learnable, yeah, then it's at most 2, right? Then it is learnable in even in an array. So it's 1 or 2. But what I wanted to say is that there are classes that satisfy item 1 that are not pack learnable. Okay,
Oh,
that's what I want to say.
I see.
Okay. Now I want, how much time do I have? I still have time, right? Like 50 minutes, Avi?
You have, yeah, till 12:30, yeah.
12:30, good, excellent. So soon we'll take a short break, but before that, I want to tell you a little bit about so like in pack learning theory, also this theory, this result, relies on a lot of combinatorics, and another interesting fact is that the algorithmic landscape is much more complex, is much richer, right? So if in pack learning we had only one universal principle of empirical risk minimization, right? Find an hypothesis that has low empirical error. Here we don't understand the landscape. We don't, in particular, we don't have a finite list of principles which is complete. But so let me tell you a little bit about the combinatorial characterization. So item 1, the exponential rate, is characterized by the existence of Littlestone trees. I will soon tell you what these are. And item 2 is characterized by the existence of VCL trees, of shattered VCL trees. This I will not tell you about, but it's similar in spirit to Littlestone trees. So what are these infinite Littlestone trees?
One question. So case 3, does that mean that there is no function R that goes to 0 such that H is learnable with universal rate R?
No, for each R, there is a hypothesis class which does not converge like R. Doesn't matter how slow you want to decay, there's something which cannot achieve this slow decay. It will be even slower.
But this says every H satisfies.
Yeah. So what Avi said is that for every R you will give me, and for every algorithm you will give me, I can find a realizable distribution on which the algorithm will be even slower than R.
Like
Okay.
if you can have a specific H that doesn't satisfy 1 or 2, you're saying that any rate slower than 1 over n is possible?
Yes, take any rate that goes arbitrarily slow to 0, 1 over log star n. If H doesn't satisfy item 1 and 2, then for any algorithm you give me that learns this H, I can find a realizable distribution on which it will decay at least as slow, even slower than 1 over log star n. Okay. No? Yes? Okay, good. So now I want to discuss the combinatorial object that characterizes those classes that can be learned in an exponential rate.
So you want to say that this generalized notion of VC dimension, I guess.
Yes, it does. It does. It does. It generalizes. We will discuss soon exactly how it does. So we will say that a class of functions AH has an infinite Lilston trees if it shatters a complete infinite decision tree. Now, what is a decision tree, right? So this is just a binary tree whose nodes, internal nodes, are associated with points from the domain, from X. And in this case, we have an infinite decision tree, so it continues forever. But of course, in computer science, we more often than not discuss finite decision trees. And notice that once I give you such a tree, every function in the world naturally defines a branch on the tree. Right? So in which way? So you test what is the value of the function on the root, on X empty sequence. If it is 0, you turn left. If it is 1, you turn right, and you continue like this iteratively. So every function defines a branch on a decision tree. And we say that H shatters this decision tree if for every node in the tree, there is a function in the class whose branch passes through this node.
And what are the Xi's? What are?
So the Xi's are, a decision tree is any such tree whose nodes correspond in some way to Xi's. If you find such a tree, if you find such a way to associate the nodes to Xi's such that the tree is shattered, such that every node is reachable by some function in the class, then we will declare that this tree is shattered by the class.
When you say complete infinite decision tree, you mean there exists a labeling of an infinite decision tree, which will be.
Exactly.
Yeah, there is a existential quantifier on placing the Xi.
Right. So H has an infinite list on tree. If there exists a way to assign to every node in the tree a point X, such that every node is reachable by some function in the class.
So I guess VC dimension is you insist that at every layer it's the same variable.
Very good. If we would insist, if we would restrict the tree so that in every layer we have the same X, right? So X0 equals X1, and here X00 equals X01 equals X10 equals X11, then if you think about it for a second, you see that you get the classical definition of shattering, like in the VC case.
So this will be the space of columns, and there will be infinite dimension.
So this is so the proposition here says that if there is no such Littlestone tree, then you can learn H in an exponential universal rate. And if there is, then you can cook a lower bound, right? So you cannot learn it faster than 1 over n. Do you want to discuss an example or okay, let me tell you a little bit about the proof overview. And if you want, later we can discuss an example. So the proof overview is as follows. So remember that in the VC case, the proof was simply uniform convergence, right? We said that there is this what you see is what you get. The empirical loss is a good proxy of the population loss, and we simply therefore any function that minimizes the empirical loss is a sound output of the algorithm. Here we do something else. So with every H, to every class H, we associate a sequential game between two players. One of them we call the learner, and the second is called the adversary. These games are, now I forgot the name, but they are played in rounds. So so each player plays they plays in consecutive rounds. So the first player starts, and then he writes something, and then the second player plays, and then the third player plays, and together they write this infinite sequence. And then based on the and so they play indefinitely, right? So think about the following game. So I play against Avi. In every round, one of us writes a digit, either 0 or 1, on the board, on the infinite board, and we play indefinitely. And then we, after we are done playing, we look at this infinite binary sequence of that we produced. If it encodes an irrational number, Avi wins, and otherwise I win. Okay, so this is the type of game we have here. And then what we show is if the adversary has a winning strategy, then there is an infinite Littleton tree, which gives us a 1 over n lower bound. And on the other case, if the learning has a winning strategy, then we get first an online learning rule for the class, and then we aggregate it using boosting techniques to get this this algorithm that enjoys this exponential learning rates.
Wait, well, how does H influence the definition of the game?
Okay, so the game actually is very simple. So let me define the game. So we have H. So let's say that you are the adversary, I'm the learner. So in each game, in each round, Avi asks me a question. He writes down xi. In the round I, he writes down xi. Xi is a point from the domain. And then I need to guess the label yi. I need to guess whether the label of xi is 0 or 1. And after I guess it, the Avi tells me whether I was wrong or right. Now, Avi is restricted as follows. At all times, the answers that Avi gives me must be consistent with a function in the class.
So in other words, I pick a decision tree, and you follow it in some path.
Very good, very good. So if we have this infinite Littleton tree that is shattered, Avi can force a mistake on every round. He will first give me the root. I will say 0, he will say, no, you are wrong, it's 1. And then he will go here to x1. And then I will guess something else. Let's say I guess 0. Let's say I guess 1. Then he would say, no, you are wrong, and we'll go here to x1, 0. And because the tree is shattered, his answers are consistent at all times with some function in class. And so what we see here is that once we have an infinite Littleton tree, then Avi has a strategy not only to force, I didn't say when I win and when Avi wins. So I win the game if I made only a finite number of mistakes. Avi wins the game in the complementing case, if he managed to force infinitely many mistakes. And what we see here is that if there exists an infinite Littleton tree, then Avi can in fact force a mistake in each and every round. So not only forces infinitely many mistakes, but I am never right, actually. And the more interesting direction is that if there is no such tree, then I have a strategy that I will make only a finite number of mistakes, as long as Avi plays fair, as long as he's always consistent with some function in the class. And the proof of the theorem exactly pivots on these two cases, right? So if Avi can win, there is a Littleton tree, and then there is a lower bound, which is also not quite trivial, the statistical lower bound, I mean. And if I can win, then we get this, first of all, this, by online learning rule, I mean a strategy that makes at most finite number of mistakes. And the final algorithm uses essentially boosts this learning rule.
A question, can you get like non-asymptotic error rates where you compute the constancy depending on the distribution P?
That's a very good question. So I'm sorry, I forget the names now. French group, Francis Bach and his group, before our paper, they showed that if you take even natural algorithms like SGD and you consider and you try to learn a linear problem like a half space with margin, they gave explicit bounds on the learning rate that depends on the margin, essentially, right? So the answer is yes. And even in some natural problems, people have shown that that these constants, they relate to how well the data is separated. But we did not touch, right? We just proved this general result. We didn't try to compute these constants for natural problems. But if you, I don't know, if you know the perceptron, for instance, then I think maybe you can reason that the perceptron has an exponential learning rate and connect the rate with the probability of getting an example in the margin or something like that. I think this should not be too hard.
Okay.
But I'm not sure. I didn't try it.
Another conceptual question is that this seems to be like separating out the role of the distribution and the class. Like the class determines the rate function and then the distribution determines the constants. But another approach would be to have like a complexity measure that mixes both the class and the distribution. So an example of this is like the uniform central limit theorem. Like we know that a class of functions will be Donsker with respect to a distribution P, if and only if the bracketing integral is finite. So in that case, like the bracketing integral mixes both the distribution and the class. I was wondering like if you could like compare these kind of approaches.
Yeah, what you suggest is very natural. So you're saying that, right, so here in a sense, we fix the class and then we quantify over realizable distributions. But you're saying that instead, maybe we can just look at a set of distributions and try to study this. So this is very interesting, but I don't know whether there is like a such a clean statement in such a setting that this trichotomy that is. But it is interesting. Yeah, it is an interesting direction. Okay. Here is let me just give you one example, one less trivial example of a class that enjoys an exponential rate. So we call it positive half spaces, right? So the domain is the natural grid in d dimensions, natural numbers in d dimensions. And we look at all indicator of half spaces whose normal vector is non-negative. So this is an example of a class that can be learned in an exponential rate. And what is also interesting about this class is that if you apply the good old empirical risk minimization principle, right? So you pick a half space which is consistent with the data, then it would be impossible for you to reach this optimal exponential rate. There will be a lower bound, I think a linear lower bound. So in order to achieve the exponential rate, you have to think outside the box, right? To do something else. In fact, you cannot even do it properly. You will have to output classifiers which are not positive half spaces in order to achieve this optimal rate.
Are you going to say something about the algorithm? I mean, how does it learn?
I'm not sure. I thought maybe to show an example, but but I do have only half an hour more, and I want to talk about the second work.
You make the decision.
I'm the boss. Okay, so let's if we have time later, then we will discuss it further. And unfortunately, I'm not with you. Otherwise, I would be happy to chat with anyone after the talk.
Are we going to take a break at all? Or are we going to go?
Okay. Yeah, let's take a break. That's an excellent idea. I'll make myself some coffee. So how long? Okay. So let's continue. So if the previous work I discussed, we kind of introduced this distribution dependent learning curve, right? So we changed the definition of learnability in a way that allows us to be more flexible and to capture distribution dependent rates. Now we are going to capture data dependent rates. And so let's okay, so what is the motivation? So in practical problems, the data often satisfies special properties that is learning, right? So one example is that despite the fact that our data as it is encoded in the computer is high dimensional, in fact, the relevant part resides on some low dimensional surface, which we don't know, of course, but it is essentially low dimensional, although the way we encode it is high dimensional. Another example is the margin, which we discussed also earlier, right? So not only, so maybe it's very high dimension, maybe the data is in very high dimension, but we have a very good separation with a large margin between the positive, the zero labeled, and the one labeled examples. So what we suggest is to capture these cases in a unified way by considering partial functions, partial concepts. So these are functions that can be undefined on part of the space. So a total concept is a total function, so it's a function from x to 0, 1. And a partial concept is a function from x to 0, 1 star, where we interpret star as being undefined. Okay? Now, once we have these partial functions, it allows us to express these data-dependent assumptions. Right? So for example, a linear classifier with large margin will just correspond to a partial concept, which on the positive side, far away from the boundary, it is positive. On the negative side, far away from the boundary, it is negative. And close to the boundary, it is undefined. And then when we get examples consistent with this partial concept, we will never see examples in the margin, close to the boundary. Same thing with a low dimensional surface, right? So we simply define such a how do you say model such a concept by having a partial concept which is defined only on the surface and is undefined elsewhere. So it's really a very simple and natural, almost obvious way to capture these assumptions.
But the distribution will be on the whole space or only on
right.
the...
So a realizable distribution is required to, so if the distribution is realizable by some particular partial function h, it cannot be supported outside the support of h. Right, so this changes the definition or this manifests itself in the definition of which distributions are realizable by the class. They must be realizable with some partial concept, which means they are also supported on the support of this partial concept. So it's really, there's nothing really clever in this thing, in this definition, but the nice thing is that it allows us, on the one hand, to express these data-dependent assumptions, such as margin, low-dimensional surfaces, etc. And at the same time, all the basic learning theoretic definitions extend naturally to partial concepts. right? So notice that we always assume that our distributions are supported on X cross 0, 1, so we never get star examples. And yeah, the error is defined in the same way. And this is what I said before. So a distribution P over examples is realizable if with probability 1, the sample that we get from this distribution, any sample of any size we get from this distribution is realizable, right? So it is in the support of some partial concept and it is labeled accordingly. Is this clear?
Yeah, but different functions in the class will have different support.
Of course, right? So even in the case of margin, right? If you look at the class of all half spaces with margin gamma. So, which means that each of them will be specified by some hyperplane and will be undefined on gamma distance from this hyperplane and will be defined according to the side on other points. And okay, good. And also the definition of pack learnability. It's defined exactly in the same way, right? So we will say that a class H of partial functions is pack learnable if there is a vanishing bound and an algorithm such that for all realizable distributions, the learning curve of the algorithm is at most these bounds, right? So all learning curves decay uniformly to 0, all realizable learning curves. Okay? It's just the same definition. I just want you to see that all the definitions extend very naturally to this context. And also the VC dimension, right? The VC dimension also extends in a natural way. It's the same definition, right? So a set of x1 up to xd will be shattered if when you look at all partial functions which are defined on x1 up to xd, then you will see all possible binary patterns. Just what Avi drew on the blackboard. Only that you ignore columns or rows. Don't remember that have stars. Is this okay?
Yeah.
Okay, good. Okay, so our partial class is more expressive, right? So other learning problems that are modeled by partial classes that cannot be modeled by total classes. So to answer this question, we need one or to formalize this question, we need the following definition. So assume we have a partial concept class H, a class of partial functions. We will say that a total concept class H prime disambiguates the partial class H if every partial concept is extended to some total concept in H prime. Right? So if you think about a partial concept class as this huge matrix which has 0, 1, and stars, to disambiguate it, you simply need to replace the stars by 0 or 1s. This is a disambiguation, right? Every partial concept is extended in some way to a total concept. And Atias, Mansour, and Kontorovich asked the following question. Is it the case that every learnable partial class can be disambiguated by a learnable total class? And in some sense, this formalizes the question whether you can model every learnable class in the partial world by a learnable class in the total world, right? So this is a formalization of the question whether the theory of partial classes is strictly more expressive. And what we showed is that the answer is yes. So there exists a pack learnable partial class H such that every H prime that disambiguates it has an unbounded VC dimension. And since we know that VC dimension characterizes learnability in the total world, then every such H prime is not PAC learnable. And moreover, I can tell you that this H prime that is the partial concept class, not only it is PAC learnable, it's PAC learnable in the strongest, in the fastest rate there can be, like VC dimension 1.
H, not H prime.
You're right, thanks. So the partial class is learnable and also as fast as PAC learnability allows us to learn. And yeah, and the proof exploits, at least to me, it was a very surprising connection with communication complexity and graph theory. And I hope to talk about it more later, although I probably won't have time. Okay, so now we reach this question that we've been pursuing. Which partial concept classes are learnable and how? So the answer to the first question is a little bit boring because it's the same answer that for total concept classes, right? So it turns out that the partial concept class H is learnable if and only if it has a finite VC dimension, and the optimal rate is really the same, D over N. However, the interesting fact is that the proof is fundamentally different than the one from total classes, right? So as you remember, for total classes, what we said is that it basically it relies on this result by Vapnik and Chervonenkis, and a sound way to learn a total class is just to output any consistent function from the class. Here, this is not the case. The proof uses graph theory. It uses an interpretation of learning algorithms as orientations of particular graphs, and there is a lot of very nice combinatorics which uses this interpretation and proves learnability. And in particular, the proof does not use, as I said, the classical, the traditional proof for total classes uses. It does not use uniform convergence and not empirical risk minimization. Okay, and now we get to the second part of our question. So are there general principles in the spirit of uniform convergence and empirical risk minimization which guide learning of partial classes? So we don't have a satisfying positive answer. We don't know of such principles, but what we can show is that these classical principles of uniform convergence and ERM are certainly not universal. They do not apply to partial classes, right? So in some sense, this PAC theory of partial classes resembles what we see in practice, that uniform convergence and ERM are not sufficient. There are problems that are learnable but cannot be learned. This is what we will show soon. Cannot be learned by empirical risk minimizers.
But you have a learning algorithm, so in some sense it is a satisfying answer. Maybe it is not encapsulated in one sentence, but there is an answer.
Yes, but we seek an answer, that will be constructive, right? That will tell you, right? So uniform convergence, right? In the total case, it's very simple, right? I just tell you, forget about all this statistical bullshit, just do optimization. You don't need to worry about all this generalization, the distribution, who cares about this? You just get your data. You want to achieve low error using a function from the restricted class on the data. So you just have an optimization problem, finding and this is a very compelling and intuitive principle. We would like to have something similar here. And the algorithm that we have that, as I said, relies on this graph theoretic perspective is sort of an abstract nonsense because it's not really practical to build this graph. So it's not really an algorithm even, it's a learning rule, I would say. It's not clear when it can be implemented efficiently. So I don't consider it a satisfying answer. It really just helps us to characterize what is that VC characterizes learnability here, but it doesn't really give a principle. Okay. Okay, so what I want to discuss next is in which sense empirical risk minimization fails. right? So remember that empirical risk minimization means that you pick a function from the class which interpolates, in the realizable case, the input data. So let's first see a very simple example, that the simplistic interpretation of ERM fails, right? So what will be the simplest interpretation of ERM? It will tell you, just pick a partial function from your class and return it as a partial function. Now, to see how this fails, take the following class. So let's take the class H, which is defined, so the domain is endpoints, consists of endpoints, and every function in the class is of the form f sub a, where a is a subset of n of size n over 2, and f sub a is 0 on points inside a, and otherwise it's undefined. So notice that this class is trivially learnable if you return the all zero function. You don't need to look at the data, just return the function that is everywhere 0, and you will have 0 error. But if you insist on being naive, on the naive ERM, then you must choose a partial function from this class. Right, so it is trivially learnable by the algorithm that outputs the all zero function. However, algorithms which are restricted to use partial functions from H need omega of n examples to guarantee error at most 1/4. And why is that? Because such an algorithm need to learn the support of the target function, which can be any subset of size n over 2. And to learn the support of a distribution over n elements requires omega of n samples. So this is the intuitive explanation, but I think this is quite convincing. Okay, but we see that this example is not really impressive, right? Because you can just output the all zero function. So how about more sophisticated ERMs? Is there a general reduction to empirical risk minimization, right? So can every learnable class H, partial class H, be learned by minimizing the empirical loss over some H prime, which is the total class? Right? Is it the case that for every partial concept class H, there is a total class H prime, such that when you apply empirical risk minimization over H prime, you learn H? Is there a reduction from learning partial concept classes to empirical risk minimization? And in the previous example we considered, the answer is yes, right? Because we said just take H prime, the class of all, this class which consists of a single function which is always 0, and if you do ERM on H prime, any algorithm that learns H prime properly will work. So the answer here is no. So there exists, and it's the same example from before, there exists a partial class H with this dimension 1, such that for every H prime, which is a total class, there exists some ERM on H prime which fails to learn H. Right? So in general, there is no reduction from learning this partial class H to empirical risk minimization over a total class H prime. Okay, and we show even more that not only the ERM fails, but in fact, in order to learn a partial class, right? So another natural question is, can we always learn a learnable partial concept class H with an algorithm that outputs simple hypotheses, right? That outputs hypotheses from a class of bounded VC dimension. Right, so informally, how many parameters are needed to represent the output hypothesis of an algorithm that learns the partial class? So again, the same example, which, as I said, builds on communication complexity, results from communication complexity, says that there exists a class H, which is learnable easily with this dimension 1, but every algorithm A that learns H if you look at the range of the algorithm, you look at all hypotheses that the algorithm might output on realizable samples, this class, this output space of the algorithm is very complicated. It has an unbounded VC dimension. Okay, so before we summarize, I want to tell you a little bit about I don't just have 5 minutes. Okay, so I won't tell you. I'll just say a couple of words. So really combinatorially, the question whose answers all these, gives all these theorems that I presented to you is the following. I'll give you a partial class, and let's just imagine a partial class as a matrix with 0, 1s, and stars. And let's assume that this partial class has VC dimension, bounded VC dimension. Let's say VC dimension 1, right? What does this mean? It means that you can never find, I don't remember what I've used, rows or columns, but you can never find, let's say, 2 rows, I think he used, in which you see all possible 4 Boolean patterns, 0, 0, 1, 0, 0, 1, and 1, 1. And the question is, can you complete the stars in this matrix to 0 or 1? Can you replace each star with either a 0 or 1, such that the VC dimension remains bounded? So maybe it will not be 1, but it will be 1,000 at most. This combinatorially, this is the heart of all of these results. Is this possible? I give you a matrix, a partial matrix. Can you complete it without increasing the VC dimension by too much? And amazingly, the answer is in general, no. There exists a matrix with VC dimension 1 such that every completion has an unbounded VC dimension. And there is this mysterious and beautiful connection to communication complexity, or the Alon-Zak-Seymour conjecture, theorem, whatever it is now, from graph theory, which we exploit. Yes, and I would have loved to show you to tell you what the Alon-Zak-Seymour conjecture is and how it relates to this result, but I don't have time. So let me just summarize, then release you to the to lunch, to the nice lunches at the IIS. Okay. So let's summarize. So progress in practical machine learning poses major challenges and interesting challenges to theory, and there is a significant effort in rethinking ML theory. However, one should not discard or cancel classical theories. And I think what we showed today is that there are natural modifications of the axiom definitions of learnability, right? You just change the order of quantifiers, you allow partial functions instead of total functions. And these very simple and natural modifications of the classical theory lead us to interesting landscapes that seem to resemble more what happens in practice, in the sense at least that ERM and uniform convergence are not universal anymore. And we still retain some of the mathematical elegance of the classical theory, and it gives us a very nice sort of ballpark to ask these questions. What are the algorithmic principles? How to learn? And maybe, and beyond, you know, the mathematical attraction that at least I have to these models, I think if we are able to answer these questions there, who knows, maybe it will be helpful even in practice. And that's it. Thank you for listening.